So from these references you can already see that most of the things we will talk about today are no textbook algorithms which you can find in the library, but this is really ongoing research, I would say. Most of this actually has been presented just this year by me at a conference in San Diego it was, I think. So you're really participating in bloody edge research here in this lecture today. This also means that the algorithms are maybe a bit more complicated and it's a bit difficult to do examples on the blackboard, but we will do our best to somehow develop these algorithms together on the blackboard. The learning targets for today is you should be able to explain what a QBF solver does, not how it works, because we will not talk about that. You should be able to explain the basic working principle of all the different approaches we are going to discuss today. You do not really have to go into all of the details and know them by heart, how exactly you have to construct all the formulas such that it works, but at least know the high-level idea of the different approaches. And finally, you should be able to give advantages and disadvantages of the different methods. So if somebody asks you on the street what is the difference and the advantages of the template-based method compared to the learning-based method, then you should be able to give an answer. Okay, so let's start by repeating what you have already discussed last week about set solvers. I'm sure you already know that set solver basically takes as input a propositional formula. A propositional formula means that all the variables in this formula are just Boolean variables, so they can be either true or false. And in addition to that, these propositional formulas must be given in so-called conjunctive normal form. You've already talked about this also last week. Does anybody recall what this means for a formula to be in conjunctive normal form? Yeah?
We have a conjunction of disjunctions.
Exactly. So, such formulas look like this. Just to repeat a little bit of terminology, because this may also be helpful for you to understand documentation of CUDD and so on for the exercises. Usually, so we have variables. In our case, they are named x1 to x3. They are all Boolean, so they can be just true or false. Then we usually say a literal is either a variable or the negation of a variable. So x1 would be a literal and also not x1 would be a literal. Now, a so-called clause is always a disjunction of literals. So this is a clause, and this is also a clause. On the other hand, a conjunction of literals will always be called a cube. Now, a CNF is always a conjunction of clauses. So, as you said, a conjunction of disjunctions of literals, basically, just as written down here. So, a set solver takes such a formula as input, and as an output, it gives us basically a yes-no answer. It tells us whether this formula is satisfiable or unsatisfiable. And usually we can also extract more information from the set solver. Usually the set solver also gives us a satisfying assignment, which means, so only in case of satisfiability of course, a satisfying assignment is just concrete values for all the variables that appear in our formula, such that this formula becomes true. So for our formula, for instance, a satisfying assignment could be set x1 to false, because this makes this clause and this clause here already true. Then we also set x3 to true, which makes also this clause here true. So all the three clauses which are conjuncted are already true. And actually x2 is completely arbitrary. You could also set it to true and would still have a satisfying assignment. In this lecture we will usually write satisfying assignments as cubes, so as conjunctions of literals. For instance, this cube here represents exactly this satisfying assignment by saying not x1 must be true, or in other words, x1 must be false, and not x2 must be true, or in other words, x2 must be false, and x3 must be true. So basically, this cube is a formula over our variables, which evaluates to true exactly for this satisfying assignment, and for every other assignment it evaluates to false. So basically this cube is just a formula representation of our satisfying assignment. And we will usually work with such formula representations of our satisfying assignments in the algorithms we will discuss later. So this was set solvers. Now what you did not hear in the previous lecture is what is a so-called QBF solver. QBF stands for quantified Boolean formulas, and this may already give you a hint of what these tools can do in addition to set solvers. So again, these solvers take as an input a propositional formula, but this time it is a quantified propositional formula, and also they require the formulas to be in a particular format, namely in so-called premix conjunctive normal form. This basically just means that we have a CNF formula as before. This is our formula phi here. And in addition to that, we can add quantifiers over the variables as a prefix. So all these Q's here are either a for-or quantifier or an existential quantifier over one of these variables. This is how a quantified propositional formula looks like in premix conjunctive normal form. So this means all the quantifiers have to be on the outermost level. We cannot mix quantifiers with formulas. All the quantifiers always talk about the entire formula, and the so-called the body of the formula, basically, this part here needs to be in CNF, just like for Satzalus. Now, I think here is also an example. It's basically the same formula as we had before, just with an additional quantifier prefix. And what this formula asks for is, it asks whether there is some value for x1, such that no matter how we choose the value for x2, we will always be able to find a value for x3, such that this formula evaluates to true. For this particular formula, this is actually the case. In general, QBF solvers also give the same feedback basically as SAT solvers. They also give us a yes-no answer to the satisfiability question, and they can also produce satisfying assignments. But here satisfying assignments are a little bit different. We just say that we can only extract satisfying assignments for the variables that are quantified existentially on the outermost level, not for the universally quantified variables, and also not for existentially quantified variables which are quantified on an inner level. Why? Well, because only for these existential variables on the outermost level we can really find one exact value. For all these other variables there is no one single value to make the formula true. For the universal variables it always must work for every value of this variable, and for such existentially quantified variables on an inner level there is also maybe not just one value, because this formula asks for all values of x2 there must exist some value for x3. But this value for x3 can be different depending on x2. So also for x3 there is not just one value to make this formula true. Actually for this example I guess there is, but in general there is not. So this is what QBF solvers do in principle. They take a formula, but similar to a SAT solver, but this time a quantified formula, and they can also say yes, no, for satisfiable or unsatisfiable, and they can also produce satisfying assignments. These two engines will be used in our synthesis algorithms now later in order to solve synthesis problems. But before we come to that, let's talk a little bit again about the concrete problem we want to solve in this lecture, and this is synthesis from safety specifications. I think in the first lecture Georg told you about the difference between safety specifications and liveness specifications, or safety properties in a specification and liveness properties in a specification. Does anybody have, again, a vague feeling of what the difference could be?
No.
Yeah?
She was first.
No, I put it properly in my wanted to say something.
Safety specifications we can evaluate if they are true in a certain amount of steps, and liveness specifications can only be evaluated when the system has stopped, so not in a given time.
Exactly, yeah. Yeah. So safety specifications typically are of this form, like they express that something bad must never happen, or that we always must remain in a good and good state or so. Whereas fairness properties usually say that something good will happen eventually at some point in the future or infinitely often, but they do not say when. It can take an arbitrary long amount of time to wait for this event. So, as you said, at no point in time we can say, now this property is really violated. It just says, at some point in the future something will happen. But if it does not happen, you never know if you just did not wait long enough, basically. So at no point in time you can detect whether a fairness property is actually violated, as you said. So, in this lecture we will focus on such pure safety specifications which can only express such things. So something bad must never happen. This may sound quite restrictive at the first glance, but actually, first of all, in realistic specifications, the biggest part of the specification is typically safety properties. So it says, if this, then this must be the case, and if this, then that must be the case, and this must never be the case, and so on. The second reason is that even if we have liveness properties, we can usually reduce them to pure safety properties. For instance, we cannot express here something like something good will happen eventually, but we can say something good will happen within the next 20 ticks. This is then a safety property. And with this trick of setting a bound on the reaction time of the system, we can always reduce liveness properties to pure safety properties. And this is actually also how certain synthesis tools work. They take a specification in LTL, for instance, and they set bounds on the reaction time for all these eventually and infinitely often operators, and thereby reduce the specification to a pure safety specification, because for safety specifications we know quite efficient algorithms that can then hopefully solve the synthesis problem more efficiently than the more complicated algorithms for all these complicated, I don't know, Rabin, Street, Büchi, generalized Büchi games and so on. Okay, so the short story, safety specifications are important also in practice, and in your exercises you will also implement a synthesis tool for pure safety specifications, but the benchmarks you have in your framework actually contain also realistic examples where they originally contained liveness properties, but these liveness properties have been transformed into pure safety specifications. More specifically, the format for our safety specifications looks as follows. So we want to synthesize reactive systems which work as follows. They have inputs and outputs, and in every time step they read input values and produce output values. Then in the next time step they read the next input, produce the next output, and this is repeated forever. Now, our specification for this lecture will look as follows. It's basically kind of an error checker which observes the inputs and the outputs of our unknown system which we want to synthesize, and it decides whether this execution it sees here is okay or not. So our specification has only one Boolean output, so to say, which has the meaning of an error bit. And the meaning is that whenever this system here violates its specification, then this error bit will go to 1. Inside of this specification we have basically a gain graph. We can also illustrate it as a circuit. And this is also how the input format in the exercises is defined. Here the specification, which basically defines the gain graph, is also given as a circuit. That's why this may also be relevant for you in the exercises. So our specification here is given in the following way. We have a couple of state bits which define in which state we are. I illustrated them here as a couple of latches which store the values of certain state bits x. Then we have a so-called transition function t, which is basically some kind of a combinational circuit which, based on the current state and the input and the output of the system, computes the next state in which we go. So this transition relation t basically encodes the transitions between the states which are allowed in our game graph. So remember that this circuit basically just defines a game graph in a clever and symbolic way. Finally, for a safety specification or for a safety game, we also need a characterization of our safe and unsafe states. And this is done by another combinational circuit, which is named P here. This is basically a function over the state bits, and it produces just one output bit, and this one output bit tells us whether this state is safe or unsafe. And the goal of synthesis in such a setting is to construct a system in such a way that the outputs are always chosen in such a way that this machine here never enters a bad state, so that this error output here never goes too high. And this is also the problem you have to solve in the exercises. This can of course be seen as a game between two players. We can see this as a game between the evil environment, which provides inputs to our system, and the good system, which controls the outputs of the system. And what we need to do is we need to find a strategy for the system player to define the outputs in such a way that this specification here never enters a bad state, so that this error output here never goes too high. The next slide shows the same information basically in a little bit more detail and also introduces some notation. So in this lecture we will always name the set of state bits x, and we will write an overline over x to indicate that this is just not just one bit, but this is a set of bits. Similar, we will write I for the vector of input bits we have and O for the vector of output bits of our system. What we are also given is a characterization of the initial states of this system, and this is given as a formula I. This formula talks about the state variables x, and this formula just evaluates to true whenever our state is in the initial state and to false otherwise. This is the usual trick of encoding sets of states using formulas. We just use a formula that evaluates to true whenever an element is in the set, and it evaluates to false whenever this element is not in the set. So here is an example. Let's say we have 5 state bits. Then if we assign a concrete value to all of these state bits, then this defines exactly one state. So this assignment to all our state bits defines a certain state named S. Now our formula I is defined in such a way that it evaluates to true for this state S if S is an initial state, and otherwise it evaluates to false. So this is how we encode sets of states symbolically using formulas. Just repeat it once more. Yeah. So in general, I don't know, as in for the exercises, there is only always exactly one initial state, but in general you may have also more initial states where the system or the specification can start. Similar to this, in the picture, the initial state is just the initial values of these flip-flops basically. Similar to that, we also have another formula. We already mentioned it briefly before. This is our so-called transition relation. As illustrated in this picture, this transition relation basically defines the next state for a given state, for a given current state, for a given input and output word, basically. Again, this is a formula over all these variables, a formula over the state variables, inputs, outputs, and next state variables, and it evaluates to true if for a certain state with a certain input and a certain output, we go into a certain next state. And it evaluates to false if we cannot go from a certain state with a certain input and a certain output to a certain next state. So this is just a formula which basically encodes all the state transitions that are possible and or not possible. What else do we have? Similar to that, we also have a formula P, also over our x variables, and this formula P characterizes our set of safe states in the same way as for I and T, basically. So in our circuit representation, this is a formula which talks about the state variables and produces just one output, and it says whether this state is safe or not. In this setting, our goal is now to construct basically a function which takes as input the states and the state variables and the inputs, and as output it produces the output of our unknown system. So what we are actually looking for is this question mark here, which defines the output of the system based on the inputs, the primary inputs of the circuit, and the current state. This is also exactly what you have to solve in the exercises. Maybe this explanation makes all this a little bit more clear. But essentially, this circuit here basically just defines a gain graph. A state, so concrete values for the x variables, is just also a state in our gain graph, and this t just defines which state transitions between the states are allowed in our gain graph. Good, so much for the problem we want to solve. Yes.
So we have here only one iteration, but in general it might be several iterations in a kind of reactive system. Or is it always one iteration?
So this thing here is just a machine that keeps on computing the next state and the next state and the next state forever. So this is not just one transition which is encoded here, but how this machine works is initially these flip-flops have a certain assign certain values for the state bits. This is our initial state. Then the machine reads a certain input word, and our system which we want to synthesize produces a certain output word, and this defines the next state. What I forgot to mention is these flip-flops have a clock, and whenever the clock ticks, the value of these variables here are taken to the output. Then this is our next state. And in the next state, the same thing happens again. The environment chooses some inputs, and the system computes some outputs, and this defines the next state. And so this is repeated, and this really basically just defines what is going on in our game graph. We start in a certain state. Let me draw this. We start in a certain state. Let's say we only have one initial state, and the one initial state is defined in such a way that all our state variables are 0. Now the environment picks some input. Let's say the input word 101. There are 3 input bits, and the environment picks this input word, and then the system picks